All right, this is a short lesson on how to solve differential equations in Maple in an extremely simple way. So in Math 176, second semester calculus, there is a section on solving ordinary differential equations, and let me explain how to do it. So first we have to define an ordinary differential equation. I'll just call it ODE, but we can call it anything we like. So let's take a simple example. Suppose this is just going to be the equation of exponential growth. So the equation is dy dx equals some constant times y. So the way we write dy dx is diff for differentiate the function y of x once with respect to x. Let's just see what that looks like, dy dx. Only I want this to be equal to, oops, let's see. Y of x comma x equals, let's say 3 times y of x. So our ordinary differential equation is dy dx is 3y of x. And you learn in calculus, even in calculus 1, that a solution of that equation is any constant times e to the 3x. So what is the command to solve a differential equation? To solve an equation itself, to solve a differential equation, it's simply dsolve. So if we say dsolve and in parentheses the equation we want to solve, this is the answer. This means C1, some constant, just one constant, times e to the 3x. So that is the general solution of this differential equation. Now, you often have a particular solution where you start with some initial condition. So I'm going to let ICS stand for initial conditions. And I could use anything. I could call it George or anything, doesn't matter. But let me say the initial condition is that y of 0 equals 7. And now, how do I solve this differential equation with this initial condition? You simply write dsolve, and in curly brackets, first the initial condition, and then the ordinary differential equation, just like that. And we should get 7e to the 3x. And that's it. That's the solution of the equation. And that is truly all there is to solving an ordinary differential equation in one variable. So just to show some examples of how nicely this works, let me do some of the problems in the text in section. So let me just write this down. So this is some problems from the textbook, section 5.2. So one differential equation is dy dx equals y plus 3. So my ordinary differential equation is going to be the derivative, differentiate y of x with respect to x one time, dy dx equals y plus 3. Right? This is problem 3 in this section. And what's the solution of this differential equation? Dsolve the ODE. Oops. Oh, I'm sorry. This should be not y, but y of x. There we are. And the solution is any constant, some constant C1 times e to the x minus 3. Well, let's do another example. Suppose we have the ordinary differential equation, dy dx equals square root of x times y. Oops, square root of x times y of x. And how do we solve that differential equation? Oh, it's some constant C1 times e to the 2/3 x to the 3/2 power. Yeah, that's what it is. Let me do one more example from section 5.2. Maybe just to label these. So this is problem 3. This was problem dy dx equals, oops. That's not where it goes. So this was the differential equation. That was the solution. And this is problem dy dx equals root x times y. This was problem 7. And that's the solution. What about problem 9? This looks more complicated. So here, the ordinary differential equation is 1 plus x squared times the derivative of y minus 2 times x times y of x equals 0. That's problem number 9. 1 plus x squared y prime minus 2xy. What's the solution? So just say dsolve, solve the differential equation, ODE, and it is x squared plus 1 times a constant plus the constant. Suppose we were at an initial condition. Suppose the initial condition were that y, let's say at 0, is equal to, I don't know, 2. And now, if we solve the differential equation with this initial condition, and this is the differential equation. Oops. That should be a comma. Now it's correct. Oops. Curly brackets. There we go. 2x squared plus 2. And you can check, if you differentiate this, you get 4x. So this says 1 plus x squared times 4x minus 2x times this. What's 2x times this? 4x cubed plus 2x. 1 plus x squared times 4x equals minus 2x times this. Right? Just check it with a pencil and paper if you like. You'll see that it works. I mean, it's one simple command and it works. Let's look at some of the problems in section 5.3. So in section 5.3, let's start with problem 1. dy dx equals x over y. So the ordinary differential equation is dy dx equals x divided by y of x. And dsolve that. And we get this answer. We get two answers. Plus or minus square root of x squared plus a constant. Let's look at problem 15. So here we have a differential equation and an initial condition. So the ordinary differential equation is y times y prime, that means y of x, times the derivative of y of x with respect to x, minus 2 times exp of x, e to the x, equals 0. Y times dy dx minus 2, and then what's the initial condition? The initial condition is that y at 0 is equal to 3. So dsolve, initial condition, ordinary differential equation. That's the answer. You'll notice when x is 0, you get the square root of 4 plus 5, which is 9. Square root of 9 is 3. And you can check by differentiating and multiplying out, just doing the work you have to do, that this is the solution. And really, Maple doesn't care how hard the problem is. It will solve them all. Let's look at problem 45. Oops. I'd rather not do 45. How about let's see. It's an interesting problem. Problem 19. That looks hard. So problem 19, we have y, which again we have to write as y of x, is that function of y, times 1 plus x squared times dy dx So this is y times 1 plus x squared times dy dx minus x times 1 plus y squared. Again, we have to write y of x squared equals 0. That is exactly the differential equation in problem 19. And the initial condition is that y of 0 is the square root of 3. Oops. So this is, I should call this is ODE. That's my differential equation. And the initial conditions, well, there's really just one. It's y of 0 equals 3. And now solve the differential equation with this initial condition. That's the answer. And again, how do you check? Well, you can check by hand. Just differentiate this, plug into this equation, do the algebra, and see that it works. Let's just do one more set of problems. This will be from section, oops, this is actually chapter 6, right? I should be saying 6.2, 6.3. So this is section 6.4. Let me just go up and correct this. This was 6.2. This 6.3. And now we're looking at section 6.4, which is very interesting. This is a certain differential equation, which is called the logistic equation, which comes up in many, many, many different examples. So let's look at some of the problems. So let's start with problem 17. So we have the following equation, and now the variable we're going to use is t instead of x, which is fine. So our ordinary differential equation in problem 17 is dy dt. So differentiate y of t with respect to t, dy dt equals y, we have to write y of t, times 1 minus y over 36. Again, we have to write y of t over 36. That's our logistic differential equation. It involves y times 1 minus something times y. And if we wanted to just solve this in general, dsolve this ordinary differential equation, we get something that looks like this, 36 times some constant. But we're given an initial condition in this problem, which is that y at time 0 is equal to 4. So now if we solve the differential equation with this initial condition, that's what we get. Notice at least when t is 0, e to the 0 is 1, so the denominator is 1 plus 8 or 9, 36 over 9 is 4. And that's what the solution looks like. Let's see if we can plot this. Suppose we plot this with respect to time. That's what it looks like. This is exactly your logistic curve. If we start at t equals 0, just plot it from 0 to 10, Nope, looks like that. No, that's what it looks like. It's exactly the kind of curve you see in the book. So this is really very nice. It just shows you how easy it is in Maple to solve hard problems in calculus. In general, solving a differential equation is difficult, but all we need to do is learn this command dsolve, define the differential equation, define the initial condition. This is the syntax, and you get the answer. And that is all there is to it.